My name is Jim Shaw, and I'm the Chief Technical Fellow here at Crystal Group. I'd like to welcome you to this podcast. We're going to have a little discussion here about heat transfer, fans and fanless designs, and what Crystal Group is doing to meet the needs for customers. I have today with me Matt Seibert, who is manager for mechanical engineering here at Crystal Group, and I have Morgan Erdel, that is the APP or Advanced Program Pursuits Manager. The discussion that we're talking about today is essentially, what are the limitations of passive versus active cooling in the designs that we're processing for either the military or heavy industrial applications. And some of the ones that come to mind and most immediately would be some of the substation power units that are IEEE 1613 requirements that have essentially a no fan requirement, or some of the more high powered applications where we're doing some AI data processing and maybe a couple of large power GPUs and some serious CPU power, and we're pulling 1,000, 1,200 watts in a system. And so with that, I'm gonna ask Matt to give us a little bit of insight into how we're dealing with these types of technologies from, let's take it from the standpoint of a high-powered application. What are some of the tools that Crystal Group uses to deal with these challenges?
Yeah, so one of the things that we look at right away is how much power do we have to dissipate and what area do we have to dissipate that power in. We'll use tools like hand calculations, spreadsheets that we've generated, and CFD analysis to be able to figure out if we can cool this application using just a finned heat structure that doesn't require fans, or if it's too much power in a highly dense area that will cause us to have to go to a fan type application.
Okay. And Morgan, did you have anything to add to that kind of thought process?
Yeah, a lot of times it'll come down to the environmental requirements for the system as well, what we have to start working with. If it needs to be a sealed unit, then we're handcuffed to a passive system. But if we have the opportunity to include fans and add airflow, then that's always going to push performance.
All right. Tell us a little bit, Morgan, about what we're doing for the thermal surveys. What is the approach that you're taking to tackle really kind of understanding the problem when you get handed a design that we need to package and ruggedize from a thermal standpoint?
Yeah, so like Matt said, you start with what is the power dissipation and the size of the unit, and that's really going to answer our question of is passive cooling an option or if we need to use fans. And then after that, we think about what are the most important requirements for the system, if weight is a concern, or what type of cold plate availability we have, and then if the chassis can be open to airflow or if it's sealed.
Yeah, that's interesting. We've done quite a few cold plate designs here recently where we've had to attack hot spots by using more of a cold plate approach where we're taking that heat right down to a sink. So that's a good comment. Matt, what are you thinking about with respect to that subject?
So yeah, that's interesting when we're talking about cold plates and how we approach the cold plate design in a passive environment. So there are tools that we can use there to help spread that heat out and get that heat to the cold plate quicker. So we'll look at things like vapor chambers and heat pipes to be able to transfer that heat from the hottest spots of the configuration directly to that cold plate and spread it over a much larger area so that we can dissipate that heat much more effectively.
Oh, good. And Morgan, I know that you've been working on heat pipes as a technology and kind of been focused on that. I think you and Matt both have. But what are your thoughts on heat pipe construction and its application in this industry, and how important is it to be vertically integrated with respect to that capability?
So incorporating heat pipes into a system help transfer the heat to a different area of the unit or dissipate the heat over a larger area, so it makes any type of finned heat sink you use, more efficient. Heat pipes historically they add cost into the unit. They add cost and complexity from a tolerance stack up and process perspective, but they do help push the performance.
Yeah, I think the other thing that they really do is they can create a significant schedule challenge as you're farming that product out to have someone do that. So that's one thing that can hamper a program's progress.
And if you're using heat pipes or a passive system, then the end orientation of the unit is important versus a fanned unit where orientation isn't as significant.
What are your thoughts, Matt?
So that's interesting in regards to orientation as well as tolerance stack up. And some of the things that we really try to focus on there is using one common mounting surface for all of those assemblies. So that way we can help reduce the amount of tolerance stack up there is, but then that way all of the heat is being sunk to one surface so that your orientation is much easier to maintain in one way.
Yeah, that's a solid approach. You're kind of driving all the tolerances to one side and taking care of it on that side, and letting the rest of the thing, the assembly float. So that's a good approach. Morgan, what are your thoughts on kind of designing from a system architecture, designing up front? When I say that, kind of understanding your requirements for passive cooling, air over fins, or complete air over components. How does that change your approach when you're trying to come up with a solid, cost-effective design with good performance?
The most cost-effective option is going to be air over components. It's the least amount of assembly and components you're including in the system. After air over components, the next most costly is air over fins. This is a nice hybrid option though if we have to work around that sealed server requirement. And adding airflow over fins is always going to increase the performance of that specific heat sink, and the more that we can increase that airflow and that air pressure, the better performance we're going to get. Then it also comes down to size of the chassis and what size of fans can we include.
Yeah. And then what about the size of the passive package relative to surface area?
Passive is always going to be limited by the natural conduction and emissivity of the material that you're using. And so you can only push a passive heat sink so far before the size of the heat sink becomes unrealistic for your application.
That's a good point, Matt. We've got some designs that we've done that are completely passive. The one that comes to mind is the SE16, which is a rugged embedded product, essentially fanless. It's all a fin design. It's relatively heavy, and correct me if I'm wrong, Matt, but I think the max CPU power for that is about 75 watts.
Yeah, and that's a fairly good size unit, and your limitation there is still just about 75 watts. And a lot of that has to do with the fact that the heat is centrally located on that unit, but at the same time it can only transfer across that aluminum to a certain extent. Now if we were to integrate heat pipes and things like that, we might be able to get a little bit better spread of that heat, but we're still fairly limited there to what the natural properties of that aluminum are. We've done a couple of other small units where we've done a very similar approach, and we're able to fit about the same amount of power into those, about 75 watts, but we're using all surfaces of that box to dissipate that heat. And there we hit our thermal limit at about 55 C.
Mm-hmm. I think, what do you guys think about taking the SE16 and applying different processor powers to that, and then simulating what the size of the unit, what would happen to the passive unit? What do you think? What do you think about that as sort of it might be an academic exercise, but it might prove the point with respect to what happens to your system. What are your thoughts?
Yeah, so that's something where we could approach it as we make the processor or the power bigger, we could increase the size of the unit. And there's a couple of different ways that we could look at that. We could look at the size of the fins, the spacing of the fins, the height of the fins, and all of those things make a big difference when it comes to the natural heat dissipating effect, or some refer to as a chimney effect, in the way that it goes up the fins and will dissipate that heat naturally. But as we increase that heat, you're going to need to increase the surface area to be able to dissipate the same amount of heat in that area.
Morgan, your thoughts?
If we apply that to a fanned server as well, and we're increasing the processor size, there are some opportunities to increase the performance, such as adding number of fans, increasing the size of the fans, or also ducting the airflow over that finned heat sink as well.
Yeah, ducting, we do a lot of ducting here. It tends to have a very pronounced effect on not wasting the airflow through the system, so we can actually do a little bit more pinpointing of where we want some mass flow. Any thoughts on that, team?
Yeah, so that's an interesting point, that when we take a fan and we apply it directly to the heat source, it's very effective. There were approaches in the past where it was more of a brute force approach, where we're trying to push as much air through the box and getting it turned over as fast as we can and circulating the air quickly. And in the new systems where we're generating much more heat in a smaller area, we take the fans and put them directly on those heat sinks using ducting, or a heat sink that already has a fan integrated into it, and we can accommodate much higher processor loads and much higher wattage processors in 2 and 3 U designs. And 1 U designs have come a long ways using ducts and fans as well.
Hey, any idea on what the current maximum CPU power draw is in a 1U, given our current architecture?
Depending on what your maximum ambient temperature is, in a 55C application, we're looking at 185 watt processors.
Okay, that's great information. I think that kind of sets the bar for the rest of the industry. And one of the things that we do here at Crystal Group is we work really hard to make sure that we have minimal pressure drop through the system, so we can maximize the mass flow rate to just get that energy out.
Yeah, something else that's really important to consider as we push the performance of 1U servers or small form factor units is you have to think about the environment outside of that specific unit. If a 1U processor, or if a 185 watt processor in a 1U is going into a rack, and you completely stack that rack full of the same server, but you don't create the environment outside the rack to cool it, the actual server isn't going to do its job.
So you're saying that system integration doesn't end at the completion of the server. You really need to look at the whole rack and make sure that it has adequate airflow.
Mm-hmm. And make sure that the required airflow can actually be provided to your unit.
Yeah, and we've been doing quite a bit more of those types of things in terms of system integration at a transit case, or that kind of rack integration. Matt, your thoughts?
So one of the things that he had brought up about pressure drop and a rack full of servers is one thing that we're cognizant of is noise often. And with a lot of pressure drop in the system, your fans will be louder. And in a 1U, you're stuck with pretty small fans, and they're loud, but it's not always just the overall volume of the noise, but it's the pitch of it as well. And with some of these high static pressure fans we're using, they have a pretty high pitched sound to them, and with a rack full of those, then you would have quite a bit of noise. So we look at that and we consider pressure drops, and we try to leave as much free airflow as we can in front and behind the fans when possible, to help reduce some of that pressure drop and quiet the fans down some.
Hey Morgan, about how much space in front of and behind the server are we looking at for this kind of airflow?
Typically around 2 inches of clearance.
Yeah, okay.
You also have to think about the cabling and what is attaching to the unit as well, because that can block airflow.
Yeah, good point. I think we're kind of coming to an end here. I think we've got a pretty good discussion going about things to think about and things that we do with respect to thermal management. I guess I'd just like to turn it back over to Morgan. Do you have anything that you wish we'd talked about here or we didn't bring up?
The last point I would like to emphasize is you really need to think about the end use application and where your system is being installed. If this is a remote area where you're not concerned about noise, or if this is next to someone's desk or in a cabin in an airplane where someone is engaging and around this unit often, that's also going to drive requirements and limitations in regard to fans.
The last point that I'd like to point out is that there is a stigma around fans and fan applications that the fan is usually the first thing to fail in a unit. And contrary to that, we use long life fans. We use fans that are well balanced, and we use a product that we have a lot of confidence in. And we have millions of hours of fans in the field, and the number of failures that we see over the last 10 years, I could count on one hand. So fan failures are very rare in our products, and they should not be something that you shy away from.
Yeah, that's a great point, Matt, because our tech services department rarely has to do anything with fans, and I do know that there are some server manufacturers that's their biggest problem. It's a testament to the thought that went into the engineering for the component selection. So it does make a difference, and you can mitigate those kinds of problems with a little forethought. So, all right, well, thank you very much. I think this has been a good podcast. I think this has been a kind of a good session, and so I'd like to welcome you out there, our audience, to reach out and ask us any questions at crystalrugged.com. And have a great day.